So we have been discussing magnetism over the last two chapters. In this chapter, we'll specifically look at magnetism that occurs naturally and what are some of its properties. In the last chapters, we discussed about the magnetic effects that arise due to the flow of current in a conductor. Over here, we have focused more on naturally occurring magnets, their properties, and how a magnetic field is different in its behavior from an electric field. So, aptly titled Magnetism and Matter. The phenomenon of magnetism was known long back. It was the Chinese where we get the first written records of naturally occurring magnets. So they were typically called lodestones. So the story goes that shepherds who used to tend sheep used to carry staff whose tips were made of metal. And whenever they used to go roaming tending the sheep, the tips of the staff used to get stuck to certain stones. And these stones were later called as lodestones. The term basically meaning a leading stone. So lodestone basically refers to the phenomenon that the stone leads, and why that is so we'll see in a further discussions. But the same phenomenon was also observed in the island of Magnesia, among the archipelago of the Greek islands. And here too, shepherds noticed a similar phenomenon. And this island has contributed the name magnet. So as people in the ancient times were intrigued with the properties of lodestone, a few of them went ahead and discovered that when a small piece of a lodestone was suspended by a string, it always used to align itself in a particular direction. It used to align itself in a particular direction. The same was also repeated by taking water in a trough and keeping a light paper or some other equivalent material and putting a bar of lodestone on top of that. Then too, the lodestone used to align itself in a particular direction. Later, when the sense of directions came to be defined as the four cardinal directions, which is north, east, west, and south, it was Chinese Emperor Huang Ti who about 4,000 years ago is credited with getting his craftsmen to design special statues which had a finger pointing arm in each of them, and the tips of these arms were all fitted with lodestones. And these were fixed on chariots. And this particular king used this unique property of lodestone, its ability to point to the same direction, to attack his enemies even when it was heavily foggy. So they used to locate their enemies even in the densest of fogs and launch surprise attacks on them, all thanks to the help given by lodestone. Hence the name leading stone or lodestone. So these were some basic phenomenon of magnets that were employed by ancient people to, in very surprising ways, to work for them. And later on in recent history, you also have what is very popular in folklore, that a piece of magnet was the first thing that intrigued Albert Einstein as a child. He was so fascinated by a piece of magnet that his dad gave, and later on he also gets a compass. And you're so intrigued by its ability to attract other things, especially metals, and point in a particular direction no matter what, that he was left wondering what causes this behavior, right? So magnetism in nature is not a very new phenomenon, but its in-depth study started mainly after the properties of magnetism were revealed by some of the early scientists who worked on current and magnetism. So it was Oersted, Ampere, Biot, Savart. Some of these key scientists led the way in trying to unravel the secrets of magnets. So what are some properties of magnets that man has been able to establish? Right. So one, he has been able to establish that our planet behaves as one giant magnet. So given its spherical shape, there exists an imaginative magnet such that the Earth has what we call a geographical north pole, and the opposite end becomes the geographical south pole, right? So the very planet on which we exist itself behaves as one giant magnet. Though the magnetic strength of this is extremely weak, nevertheless, it is this behavior of the Earth that allows lodestones to exhibit their behavior, right? So that is the second point. So magnets, when freely suspended, always point in the direction of Earth's poles, or the magnetic poles, to be more accurate. So that end of a suspended magnet that points to the geographical north is conventionally called the north pole of a magnet. And the other end, which points to the geographical south of the Earth, is called the south pole. And why do they behave this way? Because they are under the influence of the Earth's magnetic field that surrounds the Earth, right? The third aspect about magnets is that magnets, when divided, magnets when cut in half, they become two more magnets rather than their magnetic property getting destroyed. So if I have a bar magnet with a north and a south here, and I tend to cut this magnet into two pieces, then I'm left with two magnets, each having its own north and south poles, but whose magnetic strength of the field being generated by the individual magnets, they are less than the field that was being generated by both the pieces when they were together. So what we are basically saying is magnetic monopoles never exist. What's a monopole and a dipole? A dipole is what we see here. You have two poles, dipole, right? So you can never have a magnet that is just north, or you cannot have a magnet that is just south. No matter how finely I go on dividing it, I will always get a smaller magnet, but with two poles. So it's always dipole. A magnet is always dipole. There never exists a magnetic monopole, unlike charges in electricity. In electricity, you have charges which can be positive or they can be negative. This can exist separately, this can exist separately, or they can also exist as a dipole. But in magnets, that phenomenon is not observed. Fourth, a more well-known feature, like poles repel, unlike poles attract. Last one, the phenomenon that iron and its alloys can always be converted to magnets. Iron or its alloys, you can make magnets from them. And it's not some rocket science to make magnets from an iron piece. All you have to do is take an existing magnet. So you can take a needle, an existing magnet, and rub it in one direction. So that you rub it by touching it physically with the magnet and drag the magnet towards the other direction, lift it and bring it again to the starting point and repeat. When you do this about 30, 40 times, the needle becomes magnetized. And if you suspend it using a thread, you will see that it behaves exactly like the magnet that you used to magnetize it was behaving. So to represent magnetism, we in physics have developed the concept of magnetic field lines. So magnetic field lines are imaginary lines that exist in space around a magnet and which transmit the power of magnetism. And any other object that's influenced by a magnet and is in the vicinity of that magnet gets influenced because of the existence of these imaginary field lines. Now, a simple experiment that you might have performed in your lower classes is take a piece of magnet on a white sheet of paper. Place it on a white sheet of paper and you sprinkle iron filings. You sprinkle iron filings around the magnet and slightly give a few gentle tugs to the white paper. And you'll see that the magnetic field lines arrange themselves in a unique pattern, something like this. So these iron filings arrange themselves along the path of what we call the magnetic field lines. So what are properties of these magnetic field lines? So let's study some of them. So basically, if you take a magnet, I designate the top of the magnet in its current position as my north pole and the other end as south pole. And the magnetic field lines are emerging out of the north pole and emerging into or entering into the south pole. So there's one magnetic field line that goes straight, and all the other fields, they curve into the space around the pole of the magnet. So in all these cases, the magnetic field lines are moving outwards by convention, and they form perfect loops, perfect continuous closed loops between the North Pole and the South Pole. So when I do the iron filings experiment, the iron filings basically arrange themselves along these imaginary magnetic field lines, right? And the important point to remember is that they form continuous closed loops. Because it's a dipole, no loop is discontinuous. So in representation, we stop this line at this point. Actually, they form a loop of their own. Just that the further the lines move out, the weaker the magnetic force is. The second point is about the strength of these magnetic fields. So the strength is directly dependent on the density of these lines. Density of the magnetic field lines per square unit area. So if I say this to be true, then obviously you will see that at the poles, the lines are just emerging outwards and they are tightly concentrated in a smaller space. Hence, the density of the magnetic field lines is the highest at this point and the highest at this point. As you move further away from the poles, the density falls because the lines start getting spaced out, right? Hence, the greater the density of the magnetic field lines, the greater the strength of the magnetic field or the intensity of the magnetic field, which is a phenomenon you would have observed. The pole of a magnet, of a bar magnet, typically attracts a pin or any other iron object much more readily than the side of a bar magnet, right? The poles are where the magnetic property is strongly felt. The third property is magnetic field lines never intersect. Each line traces its own path and they never intersect one another. The simple reason being, if they intersect, then at the point where two lines intersect, it will be difficult to locate what will be the true north or south at that point, right? So a simple experiment again that you can do is keep a small compass at different positions along the two ends of a bar magnet and to its sides. And each time mark the direction in which the needle is pointing. You'll see that the needle's alignment goes on changing in a particular pattern. If two lines had been intersecting, there should have been some point where the needle doesn't conform to that pattern, right? So when that doesn't happen, we can easily conclude that magnetic field lines never intersect. In the previous chapter, you might recall that we had studied about solenoids. So what's a solenoid? A solenoid is a cylindrical looping of copper wire wherein the turns of the copper wire are very close to each other, right? Now, what we are about to study is that a bar magnet can be visualized as an equivalent solenoid, right? So bar magnets are something that we've all seen. A bar magnet derives its magnetic abilities naturally, whereas a solenoid carrying current derives its magnetic properties because of flowing charges through the windings of the solenoid. So now these two can be regarded as equivalent, which allows us to arrive at the magnetic field intensity of a bar magnet, starting with the assumption that it behaves like a solenoid. So if you recall, let me step back. In the previous chapter, we had studied about the magnetic field intensity at a point P on the axis of a circular loop carrying current I, we take as the starting point for deducing the magnetic field intensity of a bar magnet. Now, if I take this and extend it to a bar magnet, so I visualize the bar magnet as a solenoid over here. So let's make a few assumptions. So first, we'll assume that it carries a current I and N is the number of loops per unit length. We'll also assume the length of the bar magnet to be 2L, which means half the length is L. And I consider the central portion of the solenoid equivalent of the bar magnet to be represented by the capital letter O. The radius of this solenoid, I take it as A, small letter A. And I consider a very thin element of thickness dx, at some distance x from the central axis. And I also assume an external point P along the axis of this solenoid, which is at a distance small r from the central point O. Now, if I were to apply this to this situation, right? Apply this equation to this situation, I'll be left with the magnetic field, right? Magnetic field at point P due to this current element which loops around the solenoid as mu naught. Current that's flowing is I. But remember, we have assumed that number of loops per unit length is N. So N loops per unit length. Therefore, for a thickness of dx, the number of loops is N into dx. Right? Which is my current element, into, I'm also left with A, which is the radius of the loop over here. So the radius, in this example, the radius was capital R, whereas the radius here is A. So mu naught I n dx into A. And I also need to take the combination of all the lengths across the circumference of this solenoid. So that gives me 2 pi r, which is 2 pi r again is A over here, divided by 4 pi into x square. What is x square? X here was the distance from the central point to the point P. Here the central point is O to the point P, right? But now the central point is not here. The point I'm interested in is here. I'm interested from this point onwards. Hence, x becomes this entire distance minus this distance. So it actually becomes r minus x. So it is r minus x whole square plus r square. So plus capital R. Capital R here was the radius. So here the equivalent of capital R is A. So it is A square 3 by 2. So I can simplify this to get, so 2 pi cancels out. Here it leaves me with 2. And I'm left with mu naught by 2 into n I dx a square by r minus x whole square plus a square whole to the power 3 by 2. So what we have achieved so far is the magnetic field intensity at point P due to this current element of thickness dx that goes around our solenoid. But what we are really interested in is the magnetic field intensity at point P due to the entire bar magnet or the equivalent solenoid. So what we have to do is integrate this element of thickness dx for the entire length of the bar solenoid, which is 2L, or we can integrate it over minus L to plus L. So that gives us our magnetic intensity at point P due to the entire solenoid. So taking that further, I take the constants outside, mu naught n I a square by 2 integration minus L to plus L of dx by, since I have an x term, I can't take it outside the bracket, so I retain it inside with power 3 by 2. So now you might have realized that R is very much greater than L and R is very much greater than A for all practical purposes. So what am I trying to say? A bar magnet, its length is usually small compared to any practical distance at which we are measuring the magnetic field. So R, this distance from the center of the bar magnet to point P, is usually much, much greater than the length of the magnet itself, or half the length of the magnet for that matter. Similarly, R is also very much greater than the radius of the equivalent solenoid. So if I take both these for practical purposes, my denominator term r minus x whole square plus a square whole to the power 3 by 2 now reduces to r cube, because I ignore the x, I ignore the a. What I'm left with is r square whole to the power 3 by 2. 2 and 2 get cancelled. I'm left with r cube. So now I remove the r cube outside the integration symbol. So I'm left with mu naught n I a square by 2 r cube integration minus L to plus L of dx. So that leaves me with mu naught Ni a square into 2L by 2R cube. So when I multiply 4 pi to the numerator and denominator, I'll tend to get, so I'll just erase this portion over here. So what I get is Bp, which is equal to 4 pi n L I a square, which I group together. I keep the mu naught on one side, and the bottom I get 4 pi r cube. So I replace this with my magnetic moment, which leaves me with Bp is equal to mu naught by 4 pi into m by r cube. So this equation gives me the magnetic field at a point P, which is at the distance of small r from the center of the magnet, of the bar magnet, which behaves exactly like a solenoid of similar dimensions. Right? So Bp is equal to mu naught by 4 pi into m by r.